Graham's number is a large number that is an upper bound on the solution to a certain problem in Ramsey theory. It is named after mathematician Ronald Graham, who used the number as a simplified explanation of the upper bounds of the problem he was working on in conversations with popular science writer Martin Gardner. Gardner later described the number in Scientific American in 1977, introducing it to the general public. The number was published in the 1980 Guinness Book of World Records, which added to the popular interest in the number. Graham's number is much larger than many other large numbers such as a Google, Skewer's number and Moses' number. As with all these, it is so large that the observable universe is far too small to contain an ordinary digital representation of Graham's number. Assuming that each digit occupies one Planck volume, the smallest possible volume known to modern physics, even power towers of the form are insufficient for this purpose. Although it can be described by recursive formulas using ℏ notation or equivalent, as was done by Graham, though too large to be computed in full, many of the last digits of Graham's number can be derived through simple algorithms. The last 12 digits of 262,464,195,387 specific integers known to be far larger than Graham's number have since appeared in many serious mathematical proofs. For example, in connection with Harvey Friedman's various finite forms of Kruskal's theorem. Context: Graham's number is connected to the following problem in Ramsey theory. Connect each pair of geometric vertices of an n-dimensional hypercube to obtain a complete graph on two n vertices. Color each of the edges of this graph either red or blue. What is the smallest value of n for which every such coloring contains at least one single colored complete subgraph on four coplanar vertices? In 1971, Graham and Rothschild proved that this problem has a solution n*, giving as a bound 6n*n, with n being a large but explicitly defined number, where in ℏ notation, the number is between 4282 and 2392 in Conway chained arrow notation. This was reduced in 2014 via upper bounds on the Hales-Jewett number 2. The lower bound of 6 was later improved to 11 by Jeff Xoo in 2003, and to 13 by Jerome Berkeley in 2008. Thus, the best-known bounds for n*, 13n*n. Graham's number, g, is much larger than n, where this weaker upper bound for the problem, attributed to an unpublished work of Graham, was eventually published and named by Martin Gardner in Scientific American in November 1977. Publication. The number gained a degree of popular attention when Martin Gardner described it in the Mathematical Games section of Scientific American in November 1977, writing that Graham had recently established, in an unpublished proof, a bound so vast that it holds the record for the largest number ever used in a serious mathematical proof. The 1980 Guinness Book of World Records repeated Gardner's claim, adding to the popular interest in this number. According to physicist John Baez, Graham invented the quantity now known as Graham's number in conversation with Gardner, while Graham was trying to explain a result in Ramsey theory which he had derived with his collaborator Bruce Lee Rothschild. Graham found that the quantity now known as Graham's number was easier to explain than the actual number appearing in the proof, because the number which Graham described to Gardner is larger than the number in the paper itself. Both are valid upper bounds for the solution to the problem studied by Graham and Rothschild. Definition. Using ℏ notation, Graham's number g is where the number of arrows in each layer, starting at the top layer, is specified by the value of the next layer below it, that is, and where a superscript on an up arrow indicates how many arrows there are. In other words, g is calculated in 64 steps. The first step is to calculate G1 with 4 up arrows between 3s. The second step is to calculate G2 with G1 up arrows between 3s. The third step is to calculate G3 with G2 up arrows between 3s, and so on, until finally calculating G equals G64 with G63 up arrows between 3s. Equivalently, and the superscript on f indicates an iteration of the function, e.g., expressed in terms of the family of hyperoperations, the function f is the particular sequence, which is a version of the rapidly growing Ackermann function A. The function f can also be expressed in Conway chained arrow notation as, and this notation also provides the following bounds on G magnitude to convey the difficulty of appreciating the enormous size of Graham's number. It may be helpful to express, in terms of exponentiation alone, just the first term of the rapidly growing 64-term sequence. First, in terms of tetration operation reduces to a power tower, and then computing the nth tower in the following sequence. First tower, 3 second tower, 333 equals 7,625,597,484,987. Third tower, 3333, 3 equals G1 equals nth tower, 3, where the number of 3s in each successive tower is given by the tower just before it. Note that the result of calculating the third tower is the value of n, the number of towers for G1. The magnitude of this first term, G1, is so large that it is practically incomprehensible. Even though the above display is relatively easy to comprehend, even n, the mere number of towers in this formula for G1, is far greater than the number of Planck volumes into which one can imagine subdividing the observable universe. And after this first term, still another 63 terms remain in the rapidly growing G sequence before Graham's number G equals G64 is reached. To illustrate just how fast this sequence grows, while G1 is equal to S with only 4 up arrows, the number of up arrows in G2 is this incomprehensibly large number G1, rightmost decimal digits. Graham's number is of power tower, of the form 3n, so its rightmost decimal digits must satisfy certain properties common to all such towers. One of these properties is that all such towers of height greater than d have the same sequence of d rightmost decimal digits. This is a special case of a more general property. The d rightmost decimal digits of all such towers of height greater than d plus 2 are independent of the topmost 3 in the tower, i.e., the topmost 3 can be changed to any other non-negative integer without affecting the d rightmost digits. The following table illustrates, for a few values of d, how this happens. For a given height of tower and number of digits d, the full range of d-digit numbers does not occur. Instead, a certain smaller subset of values repeats itself in a cycle. The length of the cycle and some of the values are shown in each cell of this table. The particular rightmost d-digits that are ultimately shared by all sufficiently tall towers are 3s are in bold text, and can be seen developing as the tower height increases. For any fixed number of digits d, the number of values possible for 33, 3x mod 10d, as x ranges over all non-negative integers. A simple algorithm for computing these digits may be described as follows. Let x equals 3, then iterate d times the assignment x equals 3x mod 10d. Except for omitting any leading 0s, the final value assigned to x is then composed of the d rightmost decimal digits of 3n, for all n greater than d. Let k be the numerousness of these stable digits, which satisfy the congruence relation g, gg. K equals T1, where G equals 3T. It follows that G63 K G64. The algorithm above produces the following 500 rightmost decimal digits of Graham's number.